next talk is by Prahladh Harsha from TIFR Mumbai. We'll be hearing about solving linear high-order differential equations in nearly linear time.
Thank you. I thank the Academy for giving me an opportunity to talk. I'm Prahladh Harsha, a faculty at the School of Technology and Computer Science at TIFR Mumbai. I work primarily in theoretical computer science and mathematics. I'll be talking today on a fairly recent work done with some of my co-authors, Rohan Goyal, who's a undergrad at the Chennai Mathematical Institute, Mrinal Kumar, who's a colleague of mine at TIFR, and Ashutosh Shankar, my PhD student at TIFR. To start off with, I must confess, I am not an expert on differential equations. This is not my area of study. It so happened that a particular project which we were working on, we had to use differential equations, and in process we had to come up on some problems related to differential equations, which we solved. And I thought this will be a good place, the academy meeting, to talk about if there are other venues where our solutions could help. So, though this particular talk, I'm going to focus on the solving differential equations part of it. The work was actually a part of a larger project related to error correcting codes. We were trying to do some problem related to fast decoding of univariate multiplicity codes. This is recent work which is going to appear in a conference later this year. So for the purpose of this talk, we can ignore all of this. So let's focus on this specific smaller problem of differential equations. So as I mentioned, I'm not an expert in differential equations. If you want to have a bird's eye view, an expert's opinion, you should come to tomorrow's talk by Maithili Ramaswamy for differential equations. What I will tell is just a particular application. So what I will do in this talk are two parts to it. Firstly, I'll give you the specific problem on differential equations that we solve. I'll highlight that part of it. And then, so I'll spend first 6 or 8 minutes on the particular problem with respect to differential equations solved. And the next 8 minutes or so, I'll say the context in which this problem arose from the computer science context, and say why did differential equations actually arise there. So what's the problem? So let's actually plunge into the area and find out what's the problem that we are trying to solve. So suppose you're given some function like this. It has a specific variable x and some other variable y0, y1, y minus 1, and this happens to be such a polynomial. So it's a polynomial, it's a multivariate polynomial. The degrees in the x variables could be large, but the degrees in the y variables are all linear. It's degree 1 in each of the y variables. And what we want to solve is to find out all polynomials p of degree at most d, such that when I plug p of x, the first derivative of p of x, the second derivative of p of x, and the m minus first derivative of p of x, this equation actually identically becomes 0. So this is the usual notion of differential equations. This is a linear differential equation because all the differentials appear of degree 1, and this is what I want to solve. Of course, there are very standard methods for solving this. What I'm interested out here, we are interested in solving all polynomials p which are of utmost degree, utmost d, that solve this particular differential equation. The standard techniques following this, the particular application that we were studying with, what we wanted was actually, we not only wanted to solve this, we wanted to solve this extremely fast. And how fast? The algorithm should not take any more time, just almost time to write down the output. So it has to output a degree d polynomial, so it will take d amount of time. It has to spit out the coefficients, and it should not take significantly more time than d. That's what we want. The particular application needed this fact, and that's our basic main result. We actually give a nearly linear time algorithm, namely an algorithm that runs in time order d polylog d. So d is necessary because that's the size of the output, and the only overhead over it is our extra polylog d factor. That's basically as good as you get. This number should people familiar with arithmetic with polynomials should see this is the sort of time we take when we multiply two degree d polynomials. It simply takes time to d polylog d and stuff. So that's what we'll focus on. So what I will do in the next 5 minutes or so is sort of give an idea of why do we get a d polylog d. This one. Okay, and we're going to give a d polylog d for any high order differential equations. High order because we go up to whichever m you want. M can be 2, 3, 4, 5, whichever large constant you want, you can solve these things for all m over here. Okay, so a couple of remarks are this one. Yeah, this is something I said. We're solving it in almost just enough time to write down the answer. And other thing to notice is, that let's write down the answer. there might not be a unique answer to this problem. There could be multiple degree D polynomials that solve this particular differential equations. And when I want to answer, I want the entire space of all answers. I just don't want one single answer. In fact, if you stare at this, if the set of answers for this, set of solutions for this, set of degree D polynomials for this, which are a solution for this, actually form an affine subspace. So I want to output the entire affine subspace. Notice that it takes me time to write down even one element in the affine subspace will take me order D, and I want to output the entire affine subspace. So what we'll actually do is, if people are familiar with it, we'll actually write down, the algorithm will write down a basis for the affine subspace, which is a solution for this in order D polylog D.
So what are those IISc?
They are just arbitrary polynomials in the X. They are all polynomials. So everything out here will be polynomials, and you'll see I'll come to the application where I come from. This will be interest will be coming from polynomials underlying. These are not arbitrary functions. These are specified polynomials.
And you know them.
I know them. So the Q is completely given to me. What is not known are the P's. So you give me the A0, A1, A2 are all known given to me. I have them explicitly written down. What I don't know are the P's, and I want to find all P's. There could be several P's. For example, some of the solutions need not be polynomials. They could be infinite series which are solutions for these. What I'm interested in is only the space of polynomials which are solutions to this. Degree D polynomials which are solutions to this equation. Okay, so that's the thing I want to solve. So typically when you see with D polylog D, there's only one way D polylog D arises. Such things happens. It's the typical computer science toolkit. You take the problem, break it up into two parts which are of the same type, and recurse. This sort of thing was not used for differential equations, but what I'll show you is the same thing can be actually done over here. These are some things. So for instance, for this particular problem, there have been other approaches. There have been previously efficient polynomial time algorithms that do exactly this, except that they were polynomial time. Ours is nearly linear time. There were previous works which get, I believe it's not just Guruswami Wang, there are other, this was a reference that I found in literature. There are surely other references which also get this. Our thing will be trying to get nearly linear time. And so let's take an overview of the ODE solver which we get. So let's focus on m equal 2. Actually, I'll soon be going to even simpler case, which is m equals 1, where there's not even one differential equation, one differential operator, there's just a basic polynomial. So I want to solve this particular thing. I want to find out all P's that satisfies this. So let's ask even, do I know how to do the even more basic question, a0x plus a1 p of x? This is actually trivial. This is just division. P of x is just a0 by a1. So people never care. You don't want to really care. You can say this is just division. I don't have to do anything over here. And we do know how to do polynomial division. But polynomial division might not always be linear time. In fact, if you do the high school division, it takes quadratic time. So you would like to do it even faster. And actually, there are non-trivial methods which do this. There are several beautiful results due to Sevking, Kung, Strassen from the 70s, which are all in size a beautiful application of the standard, what we call FFT, the fast Fourier transform or Newton's iteration, which are all based on the principle of divide and conquer. And that's exactly what I want to apply for the larger than from m equals 1 to m equals 2 in logic is. So what I will try to do is, for want of time, I'll just try to give a 1 minute or 2 minute thing of the m equals 1 in the language in which we prove, so that will tell you how we could have done the m equal 2 case. So once again, I want to do this in the divide and conquer approach. So I want to find a degree D polynomial that solves this. So what we'll try to do is we'll break down this problem into trying to solve 2 degree D by 2 polynomials of a smaller type and see if we can recurse. That's going to be our goal. So what's one way of trying to lay our hands on a D by 2 polynomial? We're just going to write this polynomial P of x, the unknown polynomial P of x, as first the lower order degree D part and the higher order part of it. We just write this. We just plug it into this. We plug this thing into this and just do some. These are fairly, you just plug it into this and do the standard arithmetic. What you'll get is, if P should be a solution for this, U and V should be a solution for these two equations right at the bottom of the slide. Let me actually push it to the next slide so that it's higher up there. So if P has to be a solution for this equation, U will have to be solution to these two equations, where A0 and A1 are the same A0 and A1. B tilde is a polynomial which you can get from what you have. So what does this say? That is basically says once you have a polynomial of one type, I want to solve a degree D polynomial that resolves to solving 2 degree D by 2 polynomials, and you can now recurse. And this is basically the same central idea that goes in fast Fourier transform, and that's basically we have reduced our one problem to subproblems about half the size, together with some minimal pre and post processing, and hence the whole algorithm will run in nearly linear time using a FFT-like approach. And almost we do exactly the same thing for m equals 2. You sort of take the same approach which we said. There are some complications because the solution is not unique. The solution is an affine subspace. And these are things which are non-trivial to solve, and we do manage to solve them. So eventually, our ODE solver for a higher order, this is for m equals 0, if this is for m equals 1, for even larger ones, will essentially go along this route, but be able to solve this. Yeah, so recurse and no. Okay, so much for the ODE. Now, why did I even stumble upon this ODE? This came from an area which is very close to my heart, which is I'm a coding theorist, I work in error correcting codes a lot. So I'll tell you a problem related to error correcting codes. In particular, it will be related to noisy interpolation and noisy Hermite interpolation, and where the problem itself leads you to differential equations, and we'll stop there. So I'll end that. So let's take the next sort of 5-6 minutes to do that. So let's start off with a basic fact about polynomials. So if you take any polynomial which is a non-zero polynomial of degree d over some field. This could be the field of rationals, the field of complexes, the finite field, whichever. A basic fact about this is it can have at most d zeros. It cannot have more than d zeros. This is true because of the fact it's a field. If this were not a field, this is no longer true. Something we all take for granted, but it has some amazing properties. What are some properties of this? In other words, if you work with some field and p and q are two different polynomials, say p is not equal to q, from the field, both of them from the ring of polynomials, and both of them are of degree at most d, then the number of places where p and q can agree with each other is at most d. Because then p minus q is a non-zero polynomial. It can have at most d zeros, and the zeros exactly correspond to the locations of agreement between the two polynomials. So this is a very basic fact about polynomials. Why is this a useful fact? A consequence of this states that, suppose I give you some function from a set S to the field. I give you some function from the set S to the field, and I ask you how many polynomials agree with this function. So this is an arbitrary function. I just give you an arbitrary function. How many polynomials agree with this function? How many polynomials of degree d agree with this function on at least n plus d by 2 points? Where n is the size of the set, and at least n plus d by 2. It's not hard to see that there cannot be more than one polynomial. If there was more than one polynomial, then the two polynomials will be agreeing with each other on too many places. Because they will be agreeing with each other. If they both agree with r on n plus d by 2, you can do a simple arithmetic to check that the two polynomials themselves, say p and p prime, will agree with each other on d places, and that will be this one. So this tells you that even if somebody gives you the evaluation of the polynomial on a list of locations, but they sort of corrupt some values. Some places get corrupted. You can still recover the polynomial from it, because there's only one polynomial in that vicinity around it, therefore you have enough information to recover it. This is all combinatorial, this is all existential. The first question as a computer scientist I would like to ask is this recovery actually, can it be done algorithmic? Can I actually do the recovery in an algorithmic fashion? And why is this a useful thing? The fact that such algorithms exist are extremely important for us. In all our hard disks, this particular notion of polynomials is what leads to what are called the Reed-Solomon codes. And this is sort of the basic encoding used for all data on hard disks and stuff. So, and hard disks are physical devices. They do tend to be noisy. So every now and then, some location might get corrupted. You still want to be able to recover from it. And this is exactly this property of these polynomials of the Reed-Solomon code is what tells you that they can. So it's not just this property. We need that you can do it efficiently, and just a couple of efficiently. And there are classic algorithms from the 60s, Peterson, Berlekamp, Massey, Berlekamp-Welch, who actually solve this problem, which solve this efficiently. This one, and if you notice, if R and P, if their two polynomials agree perfect, if R and P agree everywhere, then this is just the usual interpolation. You're given a polynomial at a bunch of locations, you have to find the coefficient, that's interpolation. What we are asking here is what's called interpolation in the presence of noise. Some of the point evaluations are possibly erroneous, noise has set in, and you want to fix it. So this is what I'll call the noisy interpolation problem. And what this says is, you can do noisy interpolation as long as the number of errors is not too much. As long as the agreement is good enough, it's not perfect, but it's reasonable, you can still do it. Okay, so this is standard. This is work that's done in the 60s, 70s. What you can ask is, What about if we have more errors? This is the device which we are storing data on actually gets more errors into them. Can you still be able to recover from these? You want to tolerate even more errors. The previous, an agreement of n plus d by 2 meant errors of n minus d by 2. The space is n, therefore n minus n plus d by 2 is n minus d by 2. So previously we were able to tolerate errors as large as n minus d by 2. Question is, can you tolerate even more number of errors? Notice at this point the close-enough polynomial is no longer unique. The basic fact which I said is no longer true. There might be multiple polynomials. But as long as it's just 10 polynomials, you can say, yes, this is what the error happened, but these are these 10 polynomials nearby. I spit it out to you, and you can go and figure out which was your real data yourself. So you can ask this question. And this was actually Johnson in 62 showed that the number of such polynomials it's no longer unique, but it is a small number. It's just polynomially bounded as long as the agreement is now square root nd. Previously, the agreement was n plus d by 2. That was the arithmetic mean of n and d, in which case it's 1. It says even if we go down much smaller to the geometric mean, we will still be able to guarantee that the number of polynomials bounded is, number of close enough polynomials is small. And this was, huh? So I am going to think of n and d as comparable, so it will be polynomial in n. Yeah, it's polynomial in n. This, yeah. Sure, yeah. And okay, so once again, once we have this, you should immediately ask us, at least as a computer scientist, the first question is, can I find these polynomials efficiently? That says there are only polynomially many. Can I find them efficiently? And this actually, this is more recent work. This is work due to Madhusudan from 95 and Guruswamy and Madhusudan, who showed actually polynomial time algorithms. And in my view, these are some of the gems in theoretical computer science. It sort of led a fair amount of research in the last 20, 30 years of work. And of course, once again, these are polynomial time algorithms. These were then improved that actually you could get nearly linear time algorithms for the same setting. So far, so good. Now we can ask, okay, the Johnson bound says you can go up to so many errors. What about even more errors? Suppose your device was even more noisy. Could you still recover from these things? Could you still do recovery? And what we do, with the case of polynomials, we don't know how to do. So this is where new notion of high multiplicities and polynomials, we're going to consider polynomials which not yet vanish. We're going to consider multiplicities. That is, at every point, we're going to look at what's the number of times a polynomial vanishes at that point. We're going to look at multiplicities. More precisely, we're going to look at, we'll say a polynomial vanishes with multiplicity at least s if the polynomial, its first derivative all the way up to the s minus first derivative, all of them vanish at the point 0, the natural definition. And this is also an easy consequence. A non-zero univariate polynomial of degree d over a field s has at most d by s zeros of multiplicity s, because the total number of zeros, even counting multiplicities, is at most d. Therefore, the number of roots of multiplicity s is at most d by s. Previously, number of roots we said of multiplicity 1 was at most d. You're just going to get an extra, the number of roots is going to fall off by even further factor of s over here. So once we have this, we have a similar consequence where the agreement you're even ready. Previously, it was n plus d by 2. We were able to reduce it to even further to n plus d by s now. And now this is what is called noisy Hermite interpolation. I give you a polynomial, its bunch of list of its evaluations, its derivatives, several high order derivatives. And suppose I give you a noisy version of this, can I still recover the polynomial? And this is what Swastik Kopati and Guruswamy and Wang showed in about 10 years ago. They showed, in fact, you can do an efficient algorithm for this. And what our main result, we skip this for want of time, what our main result says is, can you do this in nearly linear time? And we do say that you can do this once again in nearly linear time, in the linear time of the output. And where does ODEs and stuff come? In the algorithm for do this, so you have some word which is a noisy polynomial and its derivatives. We construct a differential equation satisfied by all closed polynomials, and we have to solve the differential equations. And that's exactly where this comes. That more or less comes to the conclusion of my talk. So given what we have done, this is where I stumbled upon differential equations in this process. I'd like to know if these sort of linear time can extend to multivariate. We can do PDEs also. We can solve nonlinear cases. I would like to do this. And more interesting, can understand the landscape beyond the Johnson radius. I'll stop with this. Thank you.
Talk is now open for questions.
The error correcting codes,
Yeah.
they actually implemented in these standard.
Oh, the Reed-Solomon codes are what, and all your hard disk, that's what's
This
implemented.
doctor does that, is it?
Huh?
I mean, there are programs like Disk Doctor. Which
So there's this one. There is Reed-Solomon codes, and their unique decoding algorithms are implemented all the time. Each time you read your hard disk, this is what is done in practice. In those cases, we don't expect so many errors because the devices are, so the physics of devices, we understand them, they're not that noisy as before. The noise comes in places where the data is going to be very, very noisy. So you have, not in these locations, but in other places. So there are places, for example, one place where this has been studied, you send laser beams to the moon and come back. There's going to be heavy amount of noise that sets in, but you still want to be able to recover the signal. And there you use these less decoding algorithms out there. In fact, this was one actually implemented in practice.
but their polynomial time is not so important, right?
Not necessarily. If you get multiple signals, you want to keep reading them. You can't afford to spend an overhead. You have to just read the data, keep going. You keep getting signals, a zillion signals every minute, and you need to be able to go fast. Yeah.
Just a curiosity question. You said you can go to PDEs.
Yeah. No, that was something I would like to do.
Okay.
Those are, I don't know yet how to do
any
them.
type of PDEs, intersecting characteristics,
I would like
non-intersecting
to.
characteristics.
At this point, we don't have an application for it, but given that I've done this, I would like to know are there applications which need linear time PDAs? If there are, I would like to see the nature of this. So we were working with a very specific case of linear ODEs. That was this one. That was what the case, because that was necessitated by our application. It would be interesting if these techniques also hold to other cases. I don't know at this point of time.
Thank you.
If there are no more questions, please join me in thanking. Thank you.